Welcome. Thanks for joining the webinar. I will hand it firstly over to Edston, who will kick things off with the introduction.
Good evening, everyone. Hope our voice is audible. Welcome to the presentation on modeling a fall of potential earthing grid impedance test conducted by Elex Software. My name is Edson Fernandez, and I'm the lead technical researcher at Elex Software. Our presenter for today will be Mr. Jason Patrick. Jason is the technical director at Elex Software that develops leading electrical power system design and analysis software. Jason has extensive experience working on large-scale power system projects in high-voltage design, testing, commissioning, and power system analysis roles, along with 2 decades of experience in professional software development. He has a master's degree in electrical power engineering, and he leads a multidisciplinary team of developers, cloud architects, UI designers, electrical power engineers, and PhD researchers. Jason's role at Elex Software involves developing new software and complex algorithms for electrical power system design, where he is using a combination of techniques, multiple programming languages, and agile development practices. In this free webinar that is hosted by Elex Software, we will look into the principles and limitations of the fall of potential method. We will see why we have to accurately measure soil and earthing models in grid impedance testing, how softwares can help us to optimize test setups and to predict the results. During this webinar, we will show you how to simulate a fall of potential test, how soil resistivity is impacting your accuracy, and we'll also show you some practical techniques of determining optimal current and voltage electrode placements, interpreting the results, and mitigating common errors. Before I hand it over to Jason, a few housekeeping rules. I encourage you to leave your cameras on if possible so that we could have a more lively interaction. We will mute the microphones during the presentation, and feel free to send your questions, if any, on the chat, and we will answer it at the end of the webinar. If we are not able to answer it at the end of the webinar, we will send you an email with your answers at the earliest. Thank you, and I'll hand it over to Jason for the presentation.
Thank you very much, Edston. Welcome everyone to this webinar. My name is Jason Patrick. This presentation will be about earthing system modeling, testing and design. The title is Modeling a Fall of Potential Earthing Grid Impedance Test. It's a technical presentation. It's not a sales presentation. Outline of the presentation will be as follows. Why do we measure earth grid resistance? How do we do that? We will explain the fall of potential test, and we'll answer some important questions about that test, including how far away should the current electrode be placed, what direction and how far should the voltage electrode be run, what are the limitations of that test. We will talk about software modeling, how to model an earth grid resistance test using software. We will provide 2 case studies actually, and we'll examine the results of those. And finally, just to assist you in your roles in power systems, we'll provide some recommendations for earth resistance testing that you can take away with you. I'll briefly talk about SafeGrid earthing software. That software was used for the modeling. SafeGrid earthing software is finite element-based modeling software, very, very accurate and easy to use. It can model any size grid, custom grids in multi-layered soils. It can deal with below ground earthing systems or above ground earthing systems. It can calculate in the frequency domain for power system faults or in the time domain for high frequency lightning scenarios. It's fully optimized, so the calculations are efficient. It considers series impedance of grid conductors, does not assume equal potential grid conductor or grid conditions. A free trial is available of the software if you would like to try anything that we're speaking about today. The link is there. The name of the software is SafeGrid. Overview of the key points. Testing. Testing ensures safety. Testing is a very important step in earth grid design. It plays a vital role and ensures safe operation post installation commissioning. We almost always will do a current injection test or a forward potential test or both. It's questionable though. Does it really ensure 100% safety? That's a question mark for you. The follow potential test is very widely used, particularly for large and complex earthing systems. But we must remember, and I think in industry we don't really understand its limitations. And this presentation will demonstrate those important limitations that you must consider when you're using the follow potential test for your earth grid impedance measurements. Software modeling. We can use software modeling to predict the results of these follow potential tests. Or also we can predict, of course, grid impedance using a software model. It can be used at an initial stage or post installation stage during testing, during or after testing. I should also mention that there will be, I think we'll have time, there'll be a brief overview or a brief demonstration of the software and how the modeling is performed. I think Edston will jump in and do that at some point during this presentation. Why do we measure grid impedance? These are the main points taken from IEEE standard 81, just to remind us. To verify the performance of a newly installed earthing system, to detect changes in an existing system, so we can perform this test immediately after the construction of a new system or an existing system. We can use the test to determine the grid potential rise, which is another safety measure or consideration. I asked an audience last week whether there were any other reasons for doing the test, and they couldn't give me any, but perhaps if you can think of any other reasons for performing an earth grid impedance test, you could type it in the chat for everyone else. And usually, so this image here shows a software simulation on the left-hand side, and then the test measurement on the right-hand side. Normally, we go from design, simulation, modeling to the test later, but that may not always be the case. Let's talk about the actual test. The follow potential test is a very common and popular test. It has a significant advantage, theoretical advantage, practical advantage, and that's that the main advantage is that the voltage and current electrodes can have a significantly higher resistance than the grid being tested. Therefore, we're not concerned about the impedance of the leads when we are performing the test, apart from ensuring that we can supply sufficient currents being injected. A couple of assumptions are outlined here. So an assumption is that the grid itself, well, the field formed by the grid is an equivalent or an ideal hemisphere under the soil or in the soil. That's very often not the case. Grids, earthing systems are rarely symmetrical, and therefore the fields they form in the soil are almost never ideal hemispheres. And there are safety concerns with performing this test that you should consider. Lethal voltages can occur. So what's the output of a Fowler potential test? Well, it's this apparent impedance curve. So we inject current at a remote location, and we measure voltage on the surface of the ground, moving away from the grid towards the current injection point. And what we see in the plot, this is a typical Fowler potential plot. We see that voltage rises, and so too does apparent impedance as we move away from the grid. And we see towards the middle of the ideal Fowler potential test plot, we will hopefully see a flat section. And then as we move closer to the injection point, we'll see a significant rise in apparent impedance and, of course, voltage. So there is a theoretical position or location, this 61.8% or 62% rule, which is the distance away from the grid between the grid and the remote current injection point. 62% distance away from there. The apparent impedance at that distance is recognized as the so-called exact impedance. It's a simplified rule of thumb. It is mentioned in the standards, and it's quite commonly adopted. We are going to investigate whether that, during this presentation, whether that rule is actually appropriate. So let's talk about some important considerations of the Fowler potential test itself. For example, how far away should the grid, the current injection electrode, be from the grid? There are simple rules. Ideally, it should be located at an infinite distance away. That's not practical. And there is a rule. There's a couple of rules mentioned, rules of thumb mentioned in IEEE 81 and IEEE 80 they are suggesting that at least 5 times the diagonal distance of your grid, you should locate the current injection point. And that's more or less my experience, but if you'd like to share your own experience or what you think about that separation distance, you can type it in the chat for everyone else, or you can ask your questions. Now, what direction should you measure voltage? So you inject current in one direction, and you'll measure voltage away from the grid in some direction. Typically, and the most convenient direction is in the same direction as the current electrode, or where you are injecting the current. And the reason for that is that usually we need to set up some sort of temporary easement where we have run the current electrode or the current leads and set up the current electrode. So it's most practical to run the voltage measurements in the same direction, but that can lead to inaccuracies, as we will see. You can also run the voltage measurements in the opposite direction, 180 degrees away from the current electrode. And another common and often recommended direction for voltage measurements is at 90 degrees with the current electrode. And it's recommended especially when you're measuring grids that are of low impedance, so 1 ohm or less if they're expected to be of low impedance. and your software modeling would tell you that prior, that you should use the 90-degree test, and we'll get into the reasons for that. Some important recommendations here, that if you can't measure at exactly 90 degrees, then it's better that you measure at an angle greater than but less than 180 degrees, rather than between 0 and 90 degrees. Of course, these recommendations are ideal in an ideal world. If you could run your voltage and current leads in any direction you wanted, and you would set up an ideal 90-degree test. But in practical terms, it doesn't often work out like that. Let's talk again about the limitations of the Follow potential test. An ideal hemisphere is assumed for the grid itself. So that means that the grid has an electrical center, which is, again, symmetrical. Only a symmetrical grid has a real electrical, physical dimensional center. And the 61.8% rule. This rule doesn't apply in non-homogeneous soils. So it doesn't work in multi-layered soils. You shouldn't really use it other than a very rough rule of thumb. And we will show you the soil conditions where you can perhaps use it and rely on it, and where you definitely shouldn't use it or rely on it. Again, multi-layered soils, which is almost all soils have multi-layered electrical resistivity profile. This test was not developed for those to deal with those conditions, really. The mathematics behind the Follow potential test are extremely complex, even though they are quite simple, simplified or idealized. Still, the derivation is really, really complex. We won't get into it here. If you are interested, you can refer to IEEE Standard 80, and there are the original references there. You can look into the derivations. A software simulation of the earthing system and the test setup is really ideal, can easily be done with your design or modeling software. And it can predict the results of the test, and it can also provide guidance as to your test setup and where you should be running ideally the voltage electrodes or the voltage probe. So the role of software in this Follow potential or earth grid impedance testing is that it can establish or verify expected results. It can determine optimal test setup. It can test the validity of soil resistivity and earthing system models, or test those are obtained during the design phase. Also, it can verify testing results. It's highly recommended to model the Follow potential test setup for large grids or complex shapes because of that ideal hemisphere assumption of the test. Or if the soil electrical resistivity is non-homogeneous, which is almost always the case. Or an important reason to do this modeling is where you're having difficulties at site actually setting up the test. If there are limitations in running the leads, setting up a current injection point which is sufficiently far away from the grid, if there's difficulty running the voltage leads, you should do the modeling. Also, one other point is where there is significant interference expected. So from nearby earthing systems, like low voltage earthing systems, MEN systems or networks, those can cause interference, pipelines, etc., transmission lines. Doing the modeling of the test will identify inaccuracies in the actual results. So we think that it's a highly recommended thing to do. Let's look at one case study, and we'll look at two. It's a simple but not a uniform, not a symmetrical grid, but it's a medium size earthing system consistent. It's 60 meters by 30 meters. We've got lots of rods. Actually, we are assuming a sort of random 3-layer soil, 100 ohm meters in the first layer of 1 meter thickness, then a middle layer of 1 meter thickness of 200 ohm meters, and a bottom layer of infinite thickness. So we've got increasing soil electrical resistivity, a 3-layer soil model, and we've simulated this grid in the model, and we've simulated a current injection point, or we've added an electrode, and we have injected current in that point. Actually, I looked at this presentation earlier, and of course, and it's not actually 5 times the distance. So I'll need to ask the engineers how they actually did this, but it's actually more than 5 times the diagonal distance. The diagonal distance is 67 meters, and 5 times that is actually not more than 390 meters. But that's kind of irrelevant. So we set up the test in the software, and we were able to model this apparent impedance curve. And we actually tested the 61.8% rule, and we saw that 61.8% times the separation distance equated to 222 meters from the grid, and that gave us an apparent impedance of 2.5 ohms. Now the software itself can also tell us the grid impedance at more accuracy, with more accuracy. And we saw in this case a small difference between that rule of thumb, 61.8% rule, and the software modeling, 0.41% error. Now, I'll show you a case where that rule is infringed significantly. We had the same model and the same test, and in a second, I'm actually going to hand over to Edston. He's going to just show you how we actually set up this model in the software, and how we do the simulation. But in this case, we just changed the soil model. So we used a 2-layer soil model. Now that was a low resistivity on a high, so 50 ohm meters in the top layer and 2000 ohm meters in the bottom. And we saw the theoretical apparent impedance at 61.8% in comparison to the SafeGrid software actual apparent impedance. And we saw a large difference for that soil model. So at the end of the presentation, I'm going to give you some rules and some recommendations where you can perhaps use this 61.8% rule, and I'll tell you when you definitely shouldn't. Right now, I'm going to hand over to Edston. He's going to briefly show you, just for your interest, how we actually do the simulation. So can you share?
Yeah, I can. I'll send you the request. Okay. If my screen is visible.
Yes.
Hi everyone. This is a quick demo on how we could do this FOP test on SafeGrid software. I'll just take you through the important steps. This is a video that we have on our website, which every one of you can have a look at. But let me show you how this works. So the first process in SafeGrid, this is the interface that you see in SafeGrid. So you have the design settings, fault current modules, and build grid and everything. So the first initial step is to build your grid. So we have considered a simple grid, which is 60 by 30. So the diagonal length is around 67 meters. So this is a grid that we have created. There's a fault applied on the grid here, which is at this point here on the leftmost point. Now the next step to do is, as I told you, we measure the diagonal distance, which was about 65, 67 meters. We installed another current probe here, which is around 5 times 67, more than around 350 meters from the center of the grid. The center of the grid here is where the fault is applied. Now the next step is to add faults. So what we did is we added 2 faults. The first fault was on the grid, which was of 1 ampere. And the second fault was on the farther away segment, which was -1 ampere. So we were trying to simulate injecting into the main grid and getting the current out from the remote grid. So we had multiple faults here of 1 and -1 amperes. Now this, as I told you, 1 ampere is applied to the main grid and -1 ampere is applied to this remote earth point. Now the next thing to do is we go to as Jason pointed out, we are trying to find out the voltage at different points on the surface. So we create a line profile, which is from the faulted segment to the remote earth grid. Now, once we do that, we can do a calculation in SafeGrid, and the calculation tells you the surface potentials, the touch potentials, etc. So this is the ground surface voltage that you see here, and the earth grid impedance that we have calculated in the software is 2.522 at an angle 0.18 ohms. Now, to verify this, what we should do is we can download the voltages at the faulted segment. So my faulted segment is 36 here. So I can see that the voltage around that point is 2.39 ohms. So once I get that value there, so once I get that value there, what I'm primarily trying to do is I'm trying to set a constant voltage, which is the same as 2.39 that we saw earlier. We set the constant voltage so that would be my reference, and all other voltages on the surface would be a reference to that voltage. So now, because 2.39 is my reference, I can find out the voltage at each point on the ground surface with the reference to that voltage. So the next step will be to go and do a recalculation and try to find out my voltages across that point. So this is the plot that we get after recalculation, keeping 2.39 as my reference voltage. So this is the potential across the line from the faulted segment to the remote earth grid. Now, if we go through these remote points at some value of 222, which is 61.8% of 390, which is the distance between the faulted segment and the remote earth, we get a voltage of 222 meter. We get a voltage around 2.5 volt, and because the current is 1 ampere, the grid impedance would be around 2.5 ohms, which is very similar to the grid impedance that is calculated by the software. Are they not? You can see my screen? Okay. Can everyone see my screen? Is there a problem with the screen viewing?
Yes, someone else
There is an
shared the
outlook.
screen.
There is an outlook on the screen. Somebody else is sharing.
Yes, Brian is sharing the
Only
screen.
one person? Or Sorry, we are having issues with someone not able to see the screen.
No, Aston, I think anyone else took the screen, so you have to share the screen again. Yes, now
Now
we
it's
can see.
going. Can you maybe go back 1 or 2 minutes so we understand?
Okay.
Thank you.
Why don't you can share it? Okay, can you just share your screen again?
Yeah, just give me a second. Screen once. Yeah, no.
Yeah.
Is that
Is that
better,
better,
everyone?
everyone?
Yeah, yes, we can see it. But there was a lot of talking and the screen was off for a bit, so it's
So,
yeah.
Yeah, hopefully it's.
that's okay. We'll just continue.
Yeah. Okay. So yeah. So at a distance of 220 meters, we get 2.5 volts, which is the ground surface voltage. If you since the current is 1 ampere, we would obtain 2.5 ohms, which is very close to the grid impedance that has been calculated. So if we look at the exact, if you download all the potentials and you look at it, we see that we get the exact grid potential, that is 2.511, which is very close to 2.5 to what we calculated. It's between 250 to 253 meters. That's very close to our 61.88% that the theory says. So this is how we do a FOP test in SafeGrid and try to see whether the 61.8 limit is valid for our calculations. So this is the final result that we get. Theoretical 61.8, but we get approximately 62.5, very close to 61.8. Sometimes with Jason will talk next again. If you see a soil which is low on a high soil, we would see that the difference is much larger. Theoretical 61.8, but we would get only at 85.7. Some of the limitations which Jason will touch over a bit later. Thank you.
Okay. Can you see my screen?
Yeah. Yep.
Okay,
Okay,
thanks,
thanks,
Edson.
Edson.
Let's
Let's
continue.
continue.
We saw the first case study where we simulated a grid and we changed the soil model and we tested the 61.8% rule for apparent grid impedance. Case study two. Let's look at consider the effect of the leads. So in practical terms, when we do
There's a
this
lot of
test,
echo there, mate.
when we're injecting current, we run leads away from the grid to inject the current five times the at least 5 times the diagonal distance of the earthing system. So pretty far. And we also, as we're measuring voltage, we also run leads. Now,
we can't understand you.
most of us are electrical engineers here, so we understand that when we're running leads in
Hello.
parallel, we can have induced voltages, interference.
We can't understand you. You're echoing like
in
crazy.
the voltage measurement leads caused by the current, the current leads, so we can have a form of interference of the results. And this case study here will demonstrate a little bit about that. We can in the software we can simulate leads. So in the simulation that Edson just showed you, we didn't include leads. That was more or less somewhat of an ideal situation. But you can add leads. Now it's important, obviously, the relative direction. So if you're running voltage leads in the same direction as the current leads, you're going to get a different result compared to running at 90 degrees or 180 degrees. And we can see the interference. We can model that. Also, suppose that we were running in the same direction, the voltage leads as the current leads. What about the separation? So obviously, if those leads are nearer to one another, running in parallel but nearer, there'll be a higher degree of interference. So we can also simulate that. So we could say that perhaps we need to run in the same direction, our voltage measurements, but what should be the ideal or the recommended separation between those leads to minimize or to reduce interference of the voltage measurements to an acceptable level? So the first part of the test or the simulation, we ran the leads, the voltage measurement leads in the same direction as the current leads. And we can see in the top right-hand corner this plot here. So we've got the orange plot is without leads, and the blue plot is with leads. And we can see a really high distortion of the apparent impedance that's been measured. In fact, we have no flat zone. So it's really difficult or impossible in a practical sense. If we did this test practically, we would have no flat zone. So we couldn't actually determine what is the ideal apparent impedance. What's the actual apparent impedance? Because we have no flat zone. The plot on the bottom right-hand corner is a phase plot. It merely shows that the phases of the two cases, with or without considering leads, are really very, very different. And that's what causes this distortion of the apparent impedance curve. But what happens when we model the leads, but we run the voltage measurements at 90 degrees? Well, we see a really small difference. So in other words, including the leads are really having almost no effect on the result, which is a great thing. But it means that we need to run at 90 degrees. The testing measurement, the voltage measurement direction with respect to the current injection. And we can see quite good agreement with the apparent impedance phase plot in the bottom right-hand corner. Much smaller differences compared to running the leads in the same direction. So let's briefly list the recommendations for performing your Fowler potential tests that you can take away with you in your engineering work. You should extend the current injection point should be at least 5 times the diagonal distance of the grid itself, at least. If you are measuring or you expect a grid impedance measurement of 1 ohm or less, you should perform voltage measurements at 90 degrees with respect to the current electrode. Large measurement errors occur where you have long voltage measurement leads in parallel with current injection leads, particularly for low resistivity soils. To mitigate this, if you can, in a practical situation, run your measurement leads at 90 degrees, your voltage measurements. The grid impedance test should occur without the connection of overhead earth wires, excuse me, or other earthing systems connecting, other pathways in other words. You should minimize interference. And you should model your Fowler potential test setup using software before and after performing the tests to validate the results. please note and remember that the Fowler potential test is not expected to give accurate results for very large, complicated, or oddly non-symmetrical shaped grids. We believe that the 61.8% rule will give reasonable results, even for multi-layered soils, unless the soil model is low on high. We saw a very large distance. That rule will not work well in those soil conditions. And again, you can model your Fowler potential test results using software to validate your measurements. That concludes the technical presentation. Now we'll move on to your question. Edston has been curating them, and he will read them out, and we'll see if we can answer them. If not, we will definitely take note of them and get back to you with an email. So please keep sending your questions.
Okay. The first question is, when should we consider soil as non-homogeneous?
Well, you should really measure soil electrical resistivity. You should take multiple measurements, and you should have good confidence in your soil resistivity model and the measurements. It's almost never homogeneous. Almost never.
The next question is, in the case of a large-scale plant having grounding grid with more than 1 kilometer side length, how can we allocate testing probes? So even 3 times is not feasible to that stations, because of rivers and all those things. So what do we do in that?
It's tough. So you could use like an overhead line. That's what's typically used, but that requires that line to be out of service. You can use that as your remote current injection. I assume you're referring to a solar farm, probably. There is great difficulty in doing these current injection tests. What we've seen is that most people are not adhering to those separation distances because it's just simply not feasible. Almost no one is. And we expect that therefore your measurements won't be accurate. But it's a difficult situation. Certainly modeling, if you have good soil electrical resistivity results, you can certainly use modeling. And you must really use modeling to validate your tests in that case.
We've got one more question. Is why is measuring below 90 degrees not recommended?
That's a very tough mathematical question. That's covered by IEEE standard 80. If you're interested in that calculation, it's covered in there.
Now, what is the difference between above ground and below ground modeling of earthquakes?
Well, so the conductive part, obviously earthing systems or parts of earthing systems that are above the ground, those are in air. So air is virtually non-conducting. So we have series connections. So fault currents will flow in series along conductors that are above the ground, but there won't be any leakage currents from the conductor into the environments, which is different to when conductors are buried in soil. There's conductance along the conductor, and there's also leakage currents into the soil. So they're very different scenarios, and obviously a real practical earthing system consists of above ground earthing components and the below ground earthing system. But it's all really one system. So we will conclude it there.
Just one more question.
One more? Yeah.
Just one. One question is, can we do leads in SafeGrid? Can we simulate the effect of leads?
Yeah, you
Yeah, you
can.
can.
We didn't really show the test setup here, but we showed the results. Those results were taken from SafeGrid software. You can easily do it. If you're interested, you can shoot me a mail, send me an email, or you can send an email to support@elect.com. We have various technical tutorials on our website, elect.com/tutorials. There are multiple video tutorials, interactive demo tutorials at that web address. And like we said at the start, if you're interested, you can find SafeGrid at elect.com. You can request and download a free trial and use the software yourself.
Just one question is came in.
Another one?
Yeah, another one. Yeah. So the soil measurement lab tests are normally conducted at some point of the day, right?
Yeah.
So how do we compensate for other seasonal parameters on the
Good question.
Yeah, when there is.
Yeah. So, yeah, this is a very tough, important question. So soil electrical resistivity varies significantly with. Actually, it varies really significantly with temperatures, particularly low temperatures. So frozen soils, it's very, very important to understand soil electrical resistivity if you're in cold areas. But actually, it does also vary somewhat significantly with in dry areas with temperature and moisture. So if it's been raining a lot recently or not so much, there would be a conservative or an ideal time to measure soil electrical resistivity that will give you a completely different result if you'd measured it at a different time of the year. But unfortunately, in practical projects, you know, these projects and the project managers only allow us ever to go to site once. They only want to pay once to go to site. And we can't often align, we can't say to the project stakeholders, well, we need to go at a particular time when it's a really bad soil electrical resistivity. We can't do that. So there are some modeling techniques that we can apply to the soil electrical resistivity results. And we actually have built those modeling techniques. Those will actually be incorporated in our next release. So you can enter the time of year when they were measured. What else?
Rainfall, snowfall.
Rainfall data.
Precipitation data.
Precipitation
and
data.
Software selects the worst case scenario.
Yeah. And temperature. Also, it calculates soil temperature based on the time of year to give you hopefully a worst case soil electrical resistivity. So we'll be releasing, and actually there'll probably be a webinar about that.
Yeah.
Soon. Yeah, good question. Thank you. So we'll wrap it up. Thank you everyone for your questions. Thanks for your time. Thanks for joining. Thanks Edson for helping. And we will catch you on the next technical webinar. Please register for the next one. There's already one up there. I think that's about fundamentals of earthing system design, which is a really good topic. And there'll be some more webinars coming soon. Thanks everyone for your time.
Thank you.
Thank you. Cheers.
Thank you.
Thank you.